All right, I'm excited to introduce Steve Sun. He's an associate professor at Columbia University. And before that, he did his PhD at Northwestern and spent some time at Sandia National Lab. And we're all happy you made it here today.
Thank you for the introduction. So today I would like to share some of the results that we recently have. Some of them are old, some of them are newer, but I would like to first start by saying it's good to see everyone in three-dimensional. So space, which by itself is a great reward of this trip already. So before I get into the details, I would first like to acknowledge the contributions of my two students. That one did the first half of the work, Bahado Bamini on the model-free simulations, and Nicholas Venice, he did the model-based level set plasticity. So I will start by reviewing a little bit of history. So this talk is about solid mechanics simulations for path-dependent and path-independent problem using machine learning. And by using machine learning, there are already a lot of work that I just point out the timeline here. Let's see, I can. So we can see that the number of papers that actually grow up in the solid mechanics constitutive law with neural network is actually have a correlations with the economy of scale from the computer science. The AI winter may bring a lot of paper, renewed interest in using neural network to write constitutive law. And this is actually by no means a complete history of everything that are done here. But here I want to point out a few important observations before I start to motivate why we want to model the constitutive law this way. So there are lots of ways to use the neural network or actually any neural network approach to write model. We can simply use neural network to actually identify material parameter. We can do symbolic regressions. We can do recurrent neural network to predict path-dependent behavior. However, what is actually important is to create a model that can perform well with a reasonable amount of data while able to interpret the results. And this is actually particularly important for solid mechanics problem, where we are not only necessarily want to build the focusing engine, but we want to understand the mechanism. So one of our goals at the beginning is actually to create a model that are actually interpretable and yet able to deliver some robust result by leveraging our understanding on geometry. Another important observation is the time involved to create those models that are not necessarily often discussed. In general, training a neural network model is very, very easy, but training it well is very hard. So that means that, for example, in a neural network, we need to tune the hyperparameter, meaning that we need to test different architecture or different setup of neural network multiple times. And for the symbolic regressions, it's really hard to extend it to high dimensions. Most of the symbolic regressions successful story are involved one or two scalar predicting another scalar. But for our purpose of writing the constitutive law, in particular in the lack of symmetry, we need something that are able to work well when we are actually dealing with high dimensions. So this is actually the two motivations that driving force for our decision to write the model in this way. So today, I would like to have an overview of two fundamentally different approaches that are used in two different scenarios. We want to deal with the case when we don't have enough data to create a model-free approach. What is the right alternative that can allow us to create a model, a classical constitutive model that are generated with the assistance of machine learning. Another approach is actually coming from the Caltech group in 2016, is to simply abandon the effort of writing a constitutive law or simply try to matching the data. So each of them are actually useful in a different way. When we actually have a lot of data, it may be actually feasible to do the model-free approach that allow us to make prediction even without writing the model. And I will explain why this could be the case in the next slide. And then in the case where we have enough data for classical calibrations, but not enough data for big data learning, we want to create a robust neural network training that can allow us to still make predictions for some complex behavior of the solid. So I will first talk about the model-free problem, and we did it for pole mechanics, but in principle, the same idea work on also the solid mechanics problem. We just need to kill off one of the governing equations. So in a classical PDE solver for solid mechanics, we have the balance law. We actually can consider it as a manifold in E. And then we have the database. So those databases are in discrete nature. For example, we have strain and stress collect in a different frequency, and then those are the discrete point in the parametric space. And then this is actually following what the Ortiz group did, is that it constitutes a phase space we call Z. So when we actually write the boundary value problem, the classical way is to having the displacement gives us the strain, and then the strain is actually put it in the elasticity problem into some kind of model to give us a stress, and then we put it into the balance law where the divergence of stress should be zero in the absence of body force. And then this is actually the classical way to solve the problem, is to find the overlap between the constraint and the material law. Okay, so now in the case if we don't want to write a model, the continuous input mapping between the strain and stress are lost. So instead, what the original idea is actually to find the material data in each Gauss's point that minimize the distance between the constitutive law and the material data. So previously they overlap, there's no distance, because you actually also don't know the ground truth equation, but you actually guess the equations, or you actually propose the equation. But right now, you only have the database that you know is a ground truth, but they're discrete. And then you have a constitutive law that are actually defined in some smooth manifold, and then you find to minimize the distance. So this has been done in many groups since the first paper from Caltech, and we tried it. And then in the cartoon sense, it's actually this two cartoon is to compare the two. The distance minimizations measure and the continuous problem where we introduce a material constraint, and then we find the overlap versus we use the discrete data point, and then we try the distance minimizer. So the minimization problem is very simple, and then it's solved in a sequential manner. So remember, we deal with two manifolds. One is discrete, one is continuous, or more accurately, a point set and a manifold. So what we want to do is actually to solve that double minimization problem in a sequential manner. So, so the C are actually the solutions that are smooth, and they are, sorry, I need to see. The C here are the solutions that are actually fulfill the conservation law, and the D is actually the discrete data set. So we're solving this minimization problem sequentially by actually minimizing the distance that are defined in this energy norm, or actually the product norm of two energy norm in the global step, and then in the local step, we try to find the smallest distance between the data point and then the constitutive minimization solutions. And then we do this thing iteratively until we get the solutions. This could be done in single physics and multi-physics. In principle, the idea is the same. But then the questions that are actually very important is that how do we measure the distance? because the distance is actually not well defined or even it's not unique. We can use the L2 norm. We can use the H1 norm. What is the right measure for the distance? And then we can later on show that it makes a huge difference. So in terms of implementation, it's not really that complicated, but it's costly because now we have a continuous search that are actually applied on the smooth manifold. But we also have a discrete search where we want to identify individual points. We essentially need to have a ranking of the individual stress string pair and minimizing the distance, and that becomes very expensive. When we have a large database, we have a lot of data points. If you're in computer science, I guess one thing you learn the first is the ranking algorithm. So we know ranking, if you have a set of 5 elements, it's easy, you can look at it also. You can see the answer, but if you have 1 million data, how do you rank it? Okay, so this is actually a problem that actually make that very promising method become a bottleneck that need to be resolved. So this is actually some details. You can see eventually the global step governing equations look a lot like the displacement-based balance of linear equations, except that we actually have the constraint that are actually coming from minimizing the distance instead of having the stress itself. The major difference is actually on the local discrete optimizations. So in the paper that my student and I wrote, we actually introduced something from computer science, the KD tree search, basically partition the data into different dimensions, into different domains, and then using the tree structure to speed up the ranking. So basically you can see that if I actually know which zone I'm in, I can actually only search a subset of the data and then save the time. And then this can actually take out a 6.3 hours of search into 4 minutes. But then I would also be saying that in general, the discrete step is actually the speed barrier of the two methods. Again, but then you have to think about it. The numerical method doesn't require, in this case, you also don't need to write a constitutive law. Once you have the data, you can directly put it into the simulation because you already know the balance principle. So there's no effort in writing the model. Now, then we actually have some interesting discovery that are very important to share is that when we deal with multi-physics problem, how do we extend this to multi-physics problem? One important thing that is that the formulation is very simple. We can simply add another constraint and then introduce a product space. But the major challenge is the following. If I have two constitutive laws that actually map the stress strain and also the Darcy's law behavior velocity related to the parametric gradient, the two data sets have different fidelity. So if you actually, in core mechanics, you probably know, predict the permeability. If you get within the same order, you consider yourself quite accurate. But in the stress strain curve, you can actually say that I want the accuracy within 5%. It probably is doable for some simple material. They're inherently in a different level of precision. So it becomes very difficult. So our approach is simply give up in this case. So what do I mean is that if the one that with the highest, the one that actually could not be easily, the one that could be used model-based model, we will just use the model-based model. And then for the one that cannot satisfy the model-based requirement, we simply switch to the model-free. And I can show one example. So first of all, I would say to confess the following. If you're doing it in the classical displacement-based file element, the time is much faster because you don't have that discrete search that slows down the entire simulations. So the hybridizations, meaning that one part of the equation is solved in a classical displacement-based file element, and then the other part is doing that data-free modeling that doesn't require writing the constitutive law. You can see the speed up there. When you have enough data, it also calibrate well. This is a linear Tasaki problem. Of course, it do well. But also there is also another interesting aspect is this curve for the injection problem. This is actually correct result, and you can see similar result also from other group. It's actually this jump that I actually show below. Okay, so the jump is actually the non-smooth pattern of the fluid velocity is due to the fact that now your database have a discrete values of the fluid velocity, and you try to matching it. So the closest distance is actually not smooth, and hence you see that non-smooth pattern. Another thing that we can see is that if you add enough data point, eventually the different results converge, and this is actually nothing special about it. But one application that could be quite interesting is the problem that looks like this. This is actually real sandstone data. As you can see, writing the constitutive law for solid mechanics, usually the variance is very small. However, the permeability, if you actually see a permeability porosity relationships before of a real material like a sandstone, the variance is very high. So if you actually try to write a Cauchy-Kalman model or any model, you probably can capture the mean behavior pretty well, but you never hit any of those data points. So what the model free iteration allows you to do is, instead of getting the mean behavior that never actually fit the reality anyway, providing a way for you to do the overfitting where you iterate among the existing data point. So you guarantee that your fluid mechanics response is somewhat at least realistic in the sense of fitting the material data. Now, but then the recent work we extend to this work is to think back about the norm. Now, the entire algorithm depends on the distance minimizations because you are not actually simultaneously fulfilling the constitutive relationship that you derive and also the convolution. So how do you define the norm? Okay, that become very important. So in differential geometry, we know that one of the ways to define the link is use the geodesic. So here I would like to give an example just to stimulate the discussions. So this is a map. So if you want to go from Chile to Australia, I don't know exactly the city. I suppose it's Sydney and Santiago, but I could be wrong. You look at this curve, what you see is that it doesn't look like such a smart approach because I have to go all the way down and then go up again. Why is that? That is because the Earth is not flat, okay? Although K-Earthing may disagree with that, but in reality, the Earth is actually approximately spherical. So the actual shortest distance is actually the thing that we see there. The reason that we actually have the wrong perceptions is because we are in that flat surface. We are trying to use the Euclidean distance to give us a conceptual idea of what is the shortest distance. So then that actually is related to constitutive law in the sense that most of our constitutive law are nonlinear. Okay, they may not be fluctuating, but you have some kind of nonlinearity, although you cannot also see it because the dimension is higher than 3. But you can see that nonlinearity, what it translates to is that if you have a flat surface, you have one normal vector, and then in different positions, you have the same normal vector. But then if you have a curve or anything that are nonlinear, the normal direction is changing. So that makes the discrete problem very difficult. So in the approach of from UC San Diego, for example, they actually use the local point and then create a local patch. But what we're trying to do differently is the following. I actually have the conservations manifold that are actually defined as the same, but now instead of actually directly using the point, I try to learn the intrinsic property of the point that formulate a manifold. In that case, the Riemannian manifold, and then we try to actually map it onto a hyperplane. So what it means is that the machine learning, this is actually where the machine learning really happening. In the previous work, there is no even machine learning need. Here is that we try to learn the mapping that can map the nonlinear data into a flat line. So you can imagine if I have a tattoo in the hand that are actually curved, and then instead of actually trying to iterate between the nonlinear curve, I try to deform my scheme so that the tattoo that are curved appear to be straight line. And with the straight line, I can just do a projections that can very easily to get the solutions. So the machine learning we use, because we need to map it between the actual material database and then the encrypted material database, we actually have to introduce machine learning that actually guarantee the existence of the reward mapping. So we are mapping the two data. We are trying to create a mapping that F, but we also learn the G simultaneously. And we use neural network called invertible neural networks to co-chain the two mapping together. And you can see the result, and this is actually very important in the sense that, well, at least for my view, it's important. But if you use the energy norm, and then the energy norm for the nonlinear problem, that C parameter is arbitrary. It's like a stiffness, but it's not. If I choose a different energy norm, I can get a different result, map it into a different data. However, you can see C equals to 0.1, I have this mapping. C equals to 0.5, I have this mapping, and C equals to 1, I have this mapping. But in this case, when I map it into a flat surface, I have a much easier time to project the short distance for the following reason. In the flat surface, a point that are outside that flat surface, map it onto the surface, is just, you can just do a projection along the normal vector. And this is actually a very cheap calculations. You see what I mean? So if a point, I project it onto the surface, and then I will immediately get the link. This also leads to very much more robust result from the previous way. Here, I just purposely take out some data from the database so that in the model-free approach, I'm forced to make a bad choice that are in between the two string fields that have some data that are missing. Because we're learning a manifold, so if I actually missing those data, I can still using the curvature to actually guess what would be the curve that look like if I have the full data. And you can see in this 1D problem, losing some of the data doesn't immediately drive the model-free model to go crazy or generate this oscillation pattern. If you don't have the manifold intrinsic property that are actually resolved, we will actually get this oscillations pattern. So this is another example. This is just a simple trust problem. And we're trying to solve the trust system that undergo a normal vertical loading. And you can see that missing the data not only cause the predictions to be oscillating, it also causes unphysical path-dependent behavior. Whereas in these results, the result is completely smooth. In principle, this can also lead to a finite deformations results. The nice thing about this is that we only need to change the global step, but then the local step, actually the search and then the construction of manifold are actually essentially identical. Again, you can see the results. The first one is a homogeneous deformations. In our solutions, we can actually preserve the homogeneity of the solutions. You see a constant field, you don't see any spatial response. But then in the classical approach, you do see a pattern there that are non-physical. The reason is that when you lack enough data, you're forced to make some, even though I'm minimizing the distance, the earlier I'm still have a loss of distance, and then I'm forced to make some discrete choice that break the symmetry. So you can see a different problem. You can see the difference between the two. So what we translate to is that in the elasticity problem, at least based on what we study, learning the manifold and then get the intrinsic property of it help us to perform better when we don't have enough data. Because you can think about it, if I don't have any idea and then I have a curve and then I have to rely on all the data being very close to each other, so I can just use the Euclidean distance to measure the distance. But if I know the geometry, for example, if I know that I'm measuring distance on Earth or a Mars or on a surface that I know the geometry, I actually don't need that much point to get an accurate measurement on the distance. So this is a very applied way to use the differential geometry. And that doesn't only work for a model-free problem. Another thing that we want to deal with is to reconstruct the yield functions. This is, again, the problem become more complicated as we increase the dimensions. So here we don't try to do the model-free approach because for path-dependent behavior, you need a gigantic database to solve a model-free problem. Instead, we want to use the technique to do reconstructing the surface to solve the plasticity problem. So plasticity problem evolve around the dimension, in my opinion, and I think you probably also agree. Yeah, in the early plasticity, there's one invariance, which is actually the radius of the vortices. As the plasticity model get more sophisticated, you can think about it as a geometry problem. You can think about it as getting the yield surface shape and then the revolution of it getting more and more complicated over time. And then in the last 100 years, we are actually coming from vortices into critical yield surface with some fiber tensor to govern the hardening. So what we actually want to do here is that is there a generic way to do this without handcrafting everything when we see a new material, which in a sense is important because there's so many metamaterial, architecture material, new green concrete that being discovered. And then the writing an accurate model is both necessary and also increasingly difficult. So the classical way is to do the recurrent neural network, multi-step feed-forward, convolutional in 1D, we have several of them. But what we actually want to achieve is actually the model that can give us stable performance. Okay, so that means that in our approach, we go back into a more model-based, components-based philosophy. We will train the elasticity model separately. We will train the yield functions and the revolutions of the yield functions separately. And we try to see whether we can combine them into a return mapping. That brings up a lot of advantage from the geometry to predict the plasticity behavior. For example, we can say that I know that the yield surface has to be convex in order to the dissipations to be positive. And I can relay that geometry idea into predicting whether those plasticity models are physically admissible, which is not something that can be done in recurrent neural network, or we lump everything together with a big data of strain and predict the stress. So we also developed something, a small, this is a little bit small idea, but we also do it differently in the sense that we put the strain as an input and then we output the energy functional instead of directly predict the stress for the elasticity problem. Why is that? Is because we can actually get more property from both the gradient, the stiffness, and also the stress. And we can actually introduce more mechanism to check the correctness. And also one thing that I found it interesting is that when I actually increase the derivative, I actually incorporate in the learning function, in the loss functions, I actually get better results for the stress strain curve at least. Okay, so if I actually simply just minimizing the L2 norm, I actually make a bad prediction on stress, not terrible, but not so good either. And then the stiffness prediction is also not that impressive. But the interesting thing is that if I actually write the Euler functions, both in terms of the energy, the stress, and then the stiffness, I tend to get more smooth results, but more accurate results. Because I leverage not only you can think about it in a sense, if you actually try to curve fit a point, okay, you just link them together. But now I want to use the gradient. It's like I have some orientation guidance, me to draw the line together. And if I have the second derivative, I also control the curvature. So your degree of freedom with the same number of data decreasing, and that regulate the performance. We also actually try to solve the multi-objective functions in large deformations to ensure the film indifference and then the symmetric loss, symmetry loss. This is in particular important for our related work on crystal in HMX, for example, where monolithic symmetry need to be preserved, but that potentially can work for other things. So here, the symmetric loss functions would be meet any Q if this is isotropic, but would meet a subset of the Q in the special orthogonal group if the symmetry is actually, some symmetry is lost. The interesting thing about the using the energy functional is that we can also ensure that the uniqueness sensibility, which is also important when we try to learn we try to learn a machine learning model and put it in finite element. Here I calculate the acoustic tensor, and then I actually use the acoustic tensor, the smallest eigenvalue of the acoustic tensor. We draw a map of it along different orientation, and we see whether we lost the ellipticity. So if you don't do that, then you may actually predict a very good energy functional, but at some point you may actually have some vanishing wave speed, which is actually could be pretty bad for the predictions. We have a way to tune the hyperparameter, but I think that for the sake of time, I won't talk about it too much, but it can be done in reinforcement learning, and it can be done in many, many different ways. In this particular case, we use the reinforcement learning to guess what is the best optimum set of the hyperparameter to create the architecture of the neural network. There are also something that I think is interesting to solid mechanics problem, because solid mechanics problem, a lot of time dealing with stress, energy, and also the stiffness. So we need enough degree of continuity. But on the other hand, empirically, I think I speak also to some of the faculty, is in the machine learning, the ReLU have a good property, is the activation function in the neural network, but then the problem is the C0 continuity. So this one, if you take the derivative, we get a jump. So we also actually try to bypass this problem without proposing a more complicated activation functions by introducing a multiple layer. So when you train a neural network, you tune the weight and then the bias to see whether you can match a ground truth measure in the loss functions. Here, in between the two dense layer, a multi-layer perception, we add the multi-layer so that the way changing the meaning. But what it actually essentially give it to us is actually a more smooth behavior. Okay, this is actually important for solid mechanics calculations, because you can imagine that if I actually have an implicit solver, I compute the stress look really good. But if I perturb it, it suddenly oscillated, then your Newton-Raphson won't work. Okay, this is very important for convergence. So we also try to generalize the U functions, and then we use two different ways to do it. One way is actually not coming from us, but from the UK that use the NURBS basis on the point cloud of the initial U surface to create the U functions. The problem of this is that it's not easy to introduce a hardening or the change of the shape, which is important for the plasticity. Another way we try to model it is use a root base. This is by introducing a game theory, a cooperative game, which we won't talk about it here, but what we actually mentions here, the idea is the following. I introduce all the possible rules that actually I already know. And when you write the plasticity, you formulate as a game by making a sequential choice of choosing different elasticity, writing strategy, different writing U function strategy, different flow rule, and we try the best combinations. But here, that is actually possible, but it involves a discrete search again, which can be done in reinforcement learning, but in general, they're very expensive. So what we want to do is to borrow our idea on the geometry again, doing it with the level set. So remember that a U functions is actually a scalar functions that would be negative inside elastic regions and then positive outside the U function, but they're not admissible. So this is actually very close to a level set. And to evolve a level set, what we actually need is Hamilton-Jacobi equations. So what we did is a little bit like the pin, but we try to find the solutions of that Hamilton-Jacobi equation so that I can evolve the U function in any arbitrary way. So the classical way to write the U function is that I assume some change of the shape in the U functions, like isotropic hardening, I make the U function bigger. Kinematic hardening, I actually have rigid body translations of the U functions in the stress space. Or rotation hardening, I rotate the U function in the stress space. But the most general way is to define it as any arbitrary revolutions. So that means, because our current strategy we're using right now is to assume some geometrical change that are actually inspired by geometry, but we don't have to do that. We can just thinking about it as a scalar function evolve. And then we find the feature that are actually important to the predictions. So we need the data. So in the piping, this is easy because the dimension is very low. It's just 2 dimensions on the piping. We visit the initial yielding point, we construct it. And then what we actually have is this boundary. We don't know the value inside and outside, so we can define anything that is negative and positive. But what we actually want to cause the problem is to design it as a sign distance functions. So a sign distance functions is actually a scalar function where at any particular point, it gives you the values of the distance between the boundary and the current point, and then the sign that tells you whether it's inside or outside. So if this is the case, all the parasiticity model can be converted into sign distance functions. And then what we actually need to do is that we would actually need to have access to experimental data or actually have a direct numerical simulations. And then we observe how does the U surface change, because you also know that the current U surface have to remain 0. And then we can evolve that parasiticity problem by actually finding the solutions of the Hamilton-Jacobi equations in one shot. The difference between this and the pin is that in pin, you have a boundary value problem, you're using it only once. But here, once you're solving this becomes the solution of your return mapping algorithm. It provides a hardening law. It probably doesn't provide a flow rule, but we can if you choose the associated flow rule. But you can also change the plastic potential in a similar manner. So this is some example. You can do convex and non-convex. And then the Hamilton-Jacobi equations is like this. However, we can take advantage of the fact that we also don't care about the tangential flow. Okay, so this is also a small trick that makes the problem much easier because we don't care about the tangent. So we don't need the velocity, we just need the speed about in the normal directions. So we know how the U surface evolve. And then what I need to do is just learn that speed functions, which is a scalar. So the training itself is actually constituted like this. We have a U functions that can change against some internal variable, and then we can change the plastic potential this way. The upshot, so we can actually see the usage of the sign distance functions. We change the U functions and we actually keep track of how we evolve. But the most important thing is that if you look at it compared to the classical return mapping algorithm, it looks very similar. It's almost identical. The only thing it changed is the elasticity energy functional getting changed. And then the U function is defined from the machine learning. And then the tangent is obtained from the automatic differentiations. So we try this before we do anything new for the DNS simulations. We simply try the man-made problem just to ensure it's correct. You can see that the level set, the parasiticity can handle the isotropic hardening, kinematic hardening, rotational hardening, and frictional hardening. And you can also see some combinations of the U surface behavior along different directions. We compare it with the recurrent neural network that are supplied by the same data and a HyperParameter tuned. And you can see the result actually look more robust. In a sense, it's not surprising because even though the recurrent neural network actually is actually honoring the history with the memory gate and forgetting gate and some other architecture, it doesn't perform well when you have a loss of loading and unloading. Okay, this is actually, versus if you actually explicitly define the U surface, your elastic unloading is just coming from the elastic response that are very smooth. So you won't see those buckling behavior that may occur in back box neural network training. We compare it also with the convolutional 1D neural network and apply it on the polycrystal. I think the interesting thing is that we found that we can also discover use surfaces that are really hard to parameterize manually. So this is actually coming from a simulation of the polycrystal. Initially, you get something very close to a Tresca. It's not exactly a Tresca use surface on the piping, but as I share, the use surface actually have some isotropic hardening behavior, but the shape of the use surface is also distorted. As you can see here, it's not just making it bigger, and it's not only rotating, but have some combination of the response. So in this way, we can actually capture the behavior that are not necessary, that are very difficult to parameterize manually. Again, the difficulty depends on who is the modeler. Some people may have more trick to control the pattern. And then we compare that with FFT, FEM simulations, and you can see the response. One thing that we want to improve in this model is a hardening, and then also the flow rule that could be very complex for obviously more complex model. So what we actually want to address is a problem that posed by Professor Rice in his early paper in the JMPS, where he's saying that one of the obstacles of plasticity is the fact that internal variables are not physically related. So what we're actually trying to do in this granular material is to actually using some pattern as the internal variable. So in this DEM simulation, for example, we have a DEM assemble particle, and then that constitutes into a graph. The graph itself cannot directly use as the internal variable because first of all, the graph have very high dimensions. And second, it's not a vector space, so it's really hard to do regressions. I mean, there's a two social network. How do you evaluate that social network is closer to that or that relationship compared to these two family tree? Those are our graph. But one thing that we can learn from the machine learning is that we can embedding it into a vector space, meaning that we can take the graph as an input and map it into a vector space, Euclidean space in particular. So this is actually the encode feature vector. So we try to learn a machine learning, this time not directly predicting the stress, but a low order representation of this graph that are in vector space. In vector space, we have a coordinate system. We can measure how the different features are close to each other, and then we can propose a different way to learn the hardening. So this is some results. This is still done with the RNN. We have a neural results. But what we actually try to do is to use that encode feature vector associated with some pattern, which maybe I will skip this result. So this is a classical model many people use to simulate, to check whether the multi-scale implementation is correct. It's a very simple problem. We have a solid plot. I just dig a hole there. And then with that hole, I'm loading it in different way. In this case, J2 plasticity, I would predict, I would create some pattern. In this case, we have a finite element. The finite element solution are stored in a graph, and we want to perform a low dimensional embedding to actually converge it into a vector. So this is actually the result. We refine the mesh. We try to learn the embedding. Of course, when we change the nodes, the embedding would be different. But here is actually what is important is that we can use this vector space as an internal variable. We can learn the relationship between those encode feature vector and the use surface and the plastic potential. So we can using that associate with this particular pattern with the plasticity response. So the internal variable, if you use the encode feature vector as the internal variable, we can associate with it with a physical meaning. Like I know that I have more shear because that pattern emerged. Because that encode feature vector are directly associated with a pattern that are getting changed in the high dimensional space. This is done by the graph decoder. So this is the encoder architecture. So what the graph autoencoder did is the following. We take the graph as an input, we try to train it so that the output is also the same graph. But in the process of it, we try to do a data compressions. So in this part, we actually have a vector. But then the number of neurons or the design is to compress the data in the encoder regions and then unzip the data in the decoder regions. So what we actually do is to incorporate that into the training. And another promising direction is that this could always also related to the reduced dimension simulations, because you can not only do it in the passive strength field, you can also do it in the displacement field. In that case, the return mapping algorithm indirectly provide you a physical guidance on finding the patterns that are actually coming from the displacement. So we can also using this philosophy to do the reduced order modeling of the direct numerical simulation, not just to write a constitutive law. So in some sense, it kind of bridged the two unrelated field, reduced order modeling and constitutive law, into one field by using the machine learning as a group for that two things. So I personally think it's exciting, but I would say that personally, I think anything I did or my student did is exciting. At least I have to tell them so they will continue working in the world. We have to make them believe. So I would maybe how to say this, self-domesticate myself a little bit in that regard. But anyway, so but then here we try to convince you with two seemingly completely different philosophy of solving the problem. So we believe that if you have enough data, we can try model free. If not, then we try to do the model based. But in two cases, what we see very, very common is that the geometry, the understanding of the intrinsic property of the data is actually very important for us to make good and robust predictions. For example, the embedding is not only important for making the projection easier, but it can also create a new way to reduce noise. Okay, so if you have, you can think about it, if I have a curve and I have some noise, initially I would just do a Fourier decompositions. Okay, it may or may not work. But here we can introduce a new way where I bend those data into a straight line, and then I filter the data in the hyperplane and map it back into the higher dimensions. So this is done by two of my dedicated graduate students and postdoc working tirelessly for a long time. And then of course, it won't be possible without the support from our leader of the NNSA project, Richard, and also a lot of other grants that is really, I won't say that they contribute equally, but we as a group, some of the results are coming from discussions and coming from a different result, building it together. So I guess the process of doing it is very messy, so I would just keep it there. But I want to thank you for your attention, and you can find more information from our web page. I hope that, I hope that is somewhat interesting, and thank you.
Thank you for this very nice presentation. I think we're ready for questions. Any questions or comments?
Yeah, so we talked a little bit about the data smoothing.
Yeah.
So, I mean, so you want to test it out for something simple to start with, make sure it works. But
yeah.
Like considering what we're looking at for the PSAP, for example, you have potentially really large, complex data. I mean, do you have any ideas how that might work?
I think it depends on the type of data. So, for example, if it's so I think I also talked with Jeff at the morning. So my preference is that, and this is my preference, not necessarily the best approach. If you have a deformations gradient field, for example, I would first try to decomposing it into rotations and then the stress first. And then because the rotations is actually have very well established way to filtering the noise, in the sense that if you have a rotation tensor, you can map it into the, if you have a finite rotation tensor, we can map it into the Lie algebra, which is actually the skew symmetric infinitesimal string tensor, and we can filter it at the component like Euclidean space, because in the skew symmetric tensor, we only have 3 non-zero components, and we can treat it like a vector. This is actually important for filtering the noise, but you want to preserve the intrinsic property. Because if you for the rotation example, this is more than rotation, but for the rotation as example, if you filter individual components of the rotation tensor, I guarantee it will fail because rotations have a very strict meaning. So each column vector has to be orthogonal to each other and the determinant of it equals to 1. But so you need to preserve some structure. And I think this is not a necessarily good way, but there is a necessary way is to preserve those geometry, preserve those property. For the more generic case, I think you can also think about it in the geometrical sense. In the SOV is actually like a spherical. So every point in the rotation is actually a spherical. So the still symmetric tensor to the algebra is the tangential space of the Lie group. So locally they are linear, but globally they're not. So I think that what we try to do, and actually we also have another follow-up work that currently in the working is actually to find those Lie group, the algebra in general. There are some groups that are well studied, and then there are groups that are not. But we want to see whether we can use the machine learning to do a generic way. If you actually just have a constitutive law that have some intrinsic property, but they're not SO3, they're not something else, but we know it has some property, but we don't know, we cannot simply describe it. Can I actually preserve whatever property? So yeah, anyway, so sorry for the short, long answer. I hope it doesn't diverge too much, but we are thinking, long story short, I don't know what is the best way. I'm trying to find about it every day, but down the road, we need to deal with it because I think for the micromorphic, yeah, so the dimension, you can see writing the constitutive law is actually way more challenging in high dimension than in low dimension. That's why most of the handwritten constitutive law are very low dimensions. Usually 1 or 2, a PQ space, sigma 1, sigma 2, sigma 3. To handle the high dimensions, I think the machine learning is a good tool to control it. So I also even thinking about if I have all the string that are very big, I first embedding the string into 3 or 4. Maybe I can do something similar to what we already do. I mean, what we did is leverage the symmetry, basically. If I have a stress tensor, I have cosine stress, I have 6 individual components. I may compress the data, but I compress using the symmetry because I know with isotropic, I don't need 6 of them. I only need 2 of them. But I also want to see whether we can leverage as much as possible. But if you do too much, if you have isotropic material, but you have 1, then it guarantees the loss. So you see what I mean? If I have an isotropic model, but I only have Young's modulus, but I don't have Poisson ratio, it's guaranteed to be failed. So the comparison part is very challenging, I guess. But with the machine learning, you can, I guess you can say that we can try and error to see what is the right spot to compress. But I think that is important for the micromorphic. You can see how much coefficient in the tangent if you have no, if you don't have, if it's not isotropic. Even if it's isotropic, including more kinematic, definitely make it harder to control. I think that is actually purely because of the dimensionality. Or maybe there are other things as well, but also the test is harder to do. But even I'm saying, even if the test is perfect, just to deal with the dimensionality to write the model is challenging. So we also study what the handcraft model have with positivity, what with Paul statement, they have something. Usually they only have 2 invariants. They have a J2 enhanced with some scalar product of the couple stress. So we get 2 invariants. Writing high dimensional U surfaces would be very challenging.
Well, we'll find out.
You will find out how difficult it is. I guess that's the fun part. I guess the scary part is also the fun part, I think. Yeah.
Right, thanks.
Yeah.
Any other questions?
Yeah.
I was just curious about how to justify the normal norm in manifold learning. So if you go back to the matching of the discrete points to the manifold.
Yeah, that's a great question.
Yeah. What we're doing here, exactly. So what we're doing here, it appears to me, please correct me if I'm wrong, that we are minimizing the normal distance instead of minimizing the Euclidean or another solar distance like that.
Yeah.
So now the question is that are we allowed to do this?
That is actually excellent questions. This is also again from
because
the.
That may cause those buckling.
So in
learning, especially if the data spread is large.
Yeah.
And your sharing system.
So this is actually the problem studied by John Nash, the Nash embedding theory. So I'm of course not a Nash level mathematician, so but I can tell you the results of what they found, or based on the people that use the result, like your third-hand, fourth-hand information. In general, first of all, the manifold need to be smooth, so we make the assumption is smooth. In particular, a Riemannian manifold where the tangential space have an inner product that the inner product space. But the more important question is that so it's possible to embedding it while it doesn't preserve the distance. It's also in the Riemannian manifold, it's possible to embedding it while preserving the distance. It's called isometric embedding. So learning the isometric embedding is more difficult than the non-isometric, and it's actually relied on the manifold have certain property that we assume are Riemannian. Actually, Einstein's theory is on the quasi or pseudo manifold, but I won't say that I understand it, so don't get me wrong. But then the key thing here is the following. The normal vector is actually not unique. You can define anything. This is also on another related topic, because if you have a database, you want to protect the identity, and you don't want people to know what kind of data it has. So the normal vector could create a password situations where you just don't protect the normal vector, and then it will encrypt the data. Because what you see is the data here. If I take out the mapping and don't give you the normal direction, you can never have access to the true data. So this is also on another application that are very important for a company data. If you work with our company, you know how difficult to get the data. I simply need to give the user the mapping in a finite amount of time, and I just destroyed it over that, and then that you can actually forever lose the access of the data. So this is another applications that may be interesting. But you can see now I create a barrier because you don't have direct access. I'm directly dealing with this, but I rely on mapping and then the reverse mapping. But then the reverse and the mapping can be put into the cloud, and I can cut the access anytime. So I think that's another beauty of the thing, because what you need is not necessarily a particular orientation. In fact, the orientation we use is just the identity tensor. But we can try other thing. The thing is that is it possible to bend the database or the coordinate system into a flatless hypersurface? So we have more than 3 dimensions, 4 dimensions. So it's a hypersurface. So when we have the paper under review in JMPS, I think the reviewer say it's too mathematical, but the idea is very simple. If you can actually embedding it successfully on a flat surface, then you only have one normal vector. And then, anyway, so I think for the privacy thing, I think it's also quite interesting for people working at Sandia before. Also, anyway, so.
Any question?
Probably just an extension to that question. Is there anything that, as a modeler, that was intending to use this threat that I should look out for that may cause some sort of discontinuity on your intrinsic manifold, like in internal boundary conditions? What might break this that I should try and avoid?
So first of all, the manifold contains the stress string data, and then you try to learn the embedding. So if the embedding is unsuccessful, you would actually tell, because how do you change the mapping is that you try to map this data into the hypersurface so that you all have one normal vector. So in practice, you won't actually get all the arbitrary point to have a normal vector. It may be a little bit distorted, but you can capture it in the loss functions. If the loss function goes to 0, that means you successfully bend it into a hyperplane. You can think about it in that 2D problem that just like how do I actually kinematically make it flat. So if it's not successful, it will pick up in the loss functions. And then also one thing is that we are assuming that this is smooth. If it actually has very jumpy result, we can try to filter it, but then it won't work. So it's only for smooth constitutive relationships. To extend it to something that doesn't require smooth, I haven't thought about it yet, but the smoothness is actually very important to make the mapping important, because if you don't have smoothness, all the gradient, all the measure, all the control will be lost. So yeah, so we do realize smoothness. So we have a way to filter out the noise, but the mapping itself, it can be. There is also another way to use the autoencoder to filter out some of them, but then it requires more details extensions. So this is inversible, meaning that in between the forward and reverse mapping, you don't lose any information if you train it successfully, but it also means that you don't filter any noise. So this is actually for the type of simulation that have no noise, but you want to have no information loss. For the noise, we have to deal with it differently. Very obviously, you won't have a reverse mapping.
Question?
Is it the implicit assumption that all data points are of equal importance?
Oh, that is also an interesting question. We assume everything is equally important. We can create a bias, obviously, in the loss functions by saying that in certain regions is more important. I need to make sure that in this small region, nothing goes wrong. It can be done in the loss functions or do it in other way. Maybe just put more data point there. Also, I want to mention that this is not the first manifold approach. There's a Japanese paper that is right here that also deal with the manifold, but they did not map it into a hypersurface. Instead, they directly create the manifold from the point cloud using a kernel method. So that is also another way. But then the problem is that if you create the manifold to measure the distance, you have to. So let's say if you want to model the distance, you need a Riemannian matrix, and then it's in an analog, it's like you have a spherical. You make it like a soccer ball that have multiple patch, and you have to travel through the patch and then know the tangential space and add up to the length. I think this one is easier because it's globally mapped into something really fast. You don't have to think about these 2 points. I actually cause this. So in the differential geometry, it's called track. So you have it's coming from oceans explorations. You have different positions on Earth. You need to have a locally factor. You need to use the map in the right track. That kind of. Anyway, so I'm also learning from it. I wasn't trained to learn from it, but I could be wrong. So, but this is actually what I understand right now.
Question.
Yes.
For the DEM model that you turn into a graph, in order to take that graph then to oh here, yeah, in order to turn that into that graph embedding step, does this network here have to have a unique feature?
Yeah. I mean, it doesn't need to have unique feature, but then the more feature you have, you would lead to different representations. So here, the particle is the nodes, the connectivity is the edge, but the edge itself can have feature, and so does the nodes can have feature. And also, you can also put the connectivity as the nodes, and then the particle as the edge. So there are lots of different ways of doing it. And then in terms of the weight, so in the graph theory, this is called node weight, edge weight graph. So the graph has a weight, the edge has a weight. And then the weight is actually not the physical weight of the particle, but feature. So it could be the positions, obviously. It could be the size, it could be the shape, described with some descriptor. In the geometric learning paper, we wrote, because we deal with quality crystal, the orientation are the feature, but it's very flexible. But then again, the more feature you put, then the embedding will become harder. You may also need to deal with the embedding that need to deal with higher dimensions. But then the important thing for the plasticity model is that you need to carefully, and this is actually the hand graph part, you need to carefully think about what is the weight you should put in there in order to embedding it into a vector space. Because if you put the weight that are not really relevant, you can get something completely wrong. I can give you an example. For example, I can in principle put color of the particle as a weight, okay? And then I can learn the embedding. I would definitely get the embedding, but the color have nothing to do with stress strain relationships. I can paint a ball to green and then I will get a map. So that would actually lead to, you can see that from the real-time mapping, your correlation would be completely wrong and you don't see any benefit in including the graph to describe the path-dependent behavior. Or maybe accidentally you have, maybe you paint the shear band in different shape, then maybe you would. But this is actually also something that needs to be done carefully.
That's the principle of causality.
Yeah, causality. Actually, we also have another paper on causality, collaborate with John Hawkins on finding the causality of the constitutive law. In this case, we don't, this is an indirect graph, but in that case, we use the direct graph, find out what is the cause and what is the relationship. There's an algorithm to doing that. I guess the problem is also the following. Those causality relationships are usually for scalar. So to extend it to tensor require, it's not trivial, I would say. You can probably use the eigenvalues or the direction, but then the representation of it become matter, because you don't want to have a causality algorithm that depends on how you represent the tensor. But the reality is that how you represent the tensor in a spectral way, in a coordination system, it may give you different causality. So I would say causality, if it works, it helps. Actually, I have one more thing I found in causality that are very important is that for the fiber tensor, which may be relevant. And then I don't know exactly for sure, but I want maybe 10,000 of DEM. And then with the fiber tensor, what I found out, of course, is that the fiber tensor is very important to predict the stress. Everybody know that. But what I find is the following. In terms of measuring the difficulty, measuring the fiber tensor is way harder than predicting the stress. So it becomes a very interesting scenario because your intuitions is that I write a constitutive model, I know what is the physical cost, I actually simulate a physical cost, I will get the right stress. But now here, this is actually a difficult problem. If I use the causality, I would not make a forecast engine as good as I actually have the wrong causality or cost relationship, because predicting the fiber tensor is very harder, which if you think about it, it probably makes some sense because it depends on how you define the fiber tensor. Well, for what I found, and then actually I published that work, but I think nobody, my understanding is that there are probably less than 3 people read it and therefore author. So, but I would say the following. I think this is also something important that I found a constant pattern is that if you know the causality doesn't necessarily make the good predictions because of the difficulty in that causality. If you have something in between that are very hard to predict, even though you know the causality, you may better off to actually make the prediction of stress and then back calculate the fiber tensor, you may better off doing that. So that become kind of like a paradox situations that I don't have a solution, but I think it's quite interesting to find that. And that indication is actually quite strong. So this is more like a question I don't really have to answer, but maybe I also already talked too much already. But I thought about that all the time on that causality paradox that that I found it very interesting. So anyway, sorry for the very long answer.
Do you mind checking if anybody is still online and might have a question?
Sorry, I think probably not, but I don't think anyone asked questions.
Okay.
Okay.
Well, thank you again.
Okay, thank you. Yeah, thank you.